Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
For this deep dive, we've got something special for you, the learner. We're aiming to bridge two really critical worlds. First, the physical limits of material strength.
How much of a load can something actually take before it bends or breaks for good?
Exactly. And we're bridging that with the essential data for electrical components and circuits. How current flows, what the limits are, and, how fast things can burn out.
The goal here is to find the secrets to really robust electromechanical design. Because you can't design a high-power motor mount without understanding the thermal limits of the copper winding inside.
And you can't size a cable without knowing how the mechanical stress on its conduit might degrade the insulation over, say, a decade.
So let's unpack the structural side first. Let's start with how materials actually fail.
Okay, so the foundational concept here is what's called the strength of materials. It's really all about the relationship between an external force, a load, and the internal strain or deformation that results from it.
We have to define exactly where that point of no return is.
Right. And we often hear the term elasticity.
That's the ability of a material to snap back to its original shape once you remove the load.
But that ability has a very strict boundary. We call it the elastic limit. Push past that even a little, and you've got permanent damage.
And that idea leads right into yield strength, doesn't it?
It does. Yield strength is the maximum stress a part can handle without any of that permanent deformation. And for a lot of materials, we figure this out using what's called the offset method.
Right. Because some materials, like aluminum alloys, they don't have that sharp knee on their stress strain curve. It's more of a gradual bend.
Exactly. So for those, we define yield strength as the stress that results in a very specific, a definite 0.2% permanent set, a permanent strain.
Why that number? Why 0.2%? It seems so specific.
It is, and it's a critical engineering standard. It's basically the line where the material has stretched just enough that even though it hasn't broken, it's now useless for any kind of precision function. It's a standardized, repeatable benchmark.
I see. So engineers all over the world can use it to compare specs and guarantee reliability.
Precisely. Especially for things like, highly stressed aircraft parts or machinery that just cannot afford any permanent dimensional change.
Okay, so that's the limit for a single static load. But what about when a load just sits there for a long time, or when it cycles over and over?
Right, that brings up two time-dependent failure modes. Let's start with cold flow.
Cold flow, it sounds a bit strange.
It's insidious. It happens without any heat or stress cycling. It's just a slow, gradual deformation under a constant load. You see it a lot in non-elastic materials.
Like soft metals or certain plastics. I've heard Teflon is a classic example.
Teflon is a perfect example. The material basically, it oozes out from under the pressure over time.
So if you're using it for a seal, that slow creep means your seal is going to fail eventually, even if the pressure never once changed.
That's it. And that's why good designers compensate for it. They'll often use spring loading in the fixture to maintain a constant sealing pressure, even as the material itself is slowly flowing.
Okay, so the other time-dependent failure is fatigue. Now, this is the one that really keeps structural engineers up at night.
It is. This is breaking caused by repeated loads, even when those loads are way, way below the material's static yield strength.
And the key concept here is the fatigue endurance limit.
Yes. This is the magic number. It's the point where the relationship between the stress and the lifespan of the part suddenly stabilizes. Any load applied below this limit can, in theory, be applied an infinite number of times without the part ever breaking.
So finding that limit is everything in durability testing. If you design below it, you've essentially built in a perpetual service life for normal operation.
You've got it.
Okay, let's scale up. Let's talk about larger structures, like beams. Here, the basic mechanics all come down to the conditions of equilibrium.
Correct. For any static structure, we really only rely on two fundamental conditions. First, the algebraic sum of all the vertical forces has to equal 0.
Which means, in practice, all the forces pushing down loads, plus the beam's own weight, have to be perfectly balanced by the upward forces from the supports, R1 plus R2.
Exactly. And you'd be surprised how often the beam's own weight is overlooked. Or in really large structures, it becomes the dominant factor.
The second condition is about rotation, isn't it?
It is. The algebraic sum of the moments of all those vertical forces must also equal 0. When you calculate these forces, you can generate something called a moment diagram.
And that moment diagram is the real treasure map for a designer.
It really is. It points you to the dangerous section. That's the one cross-section where the internal bending moment and therefore the stress is at its absolute greatest.
For a simple beam with an even load, that's right in the middle, right?
Smack in the center. And knowing that exact spot is vital because that's where you need to ensure you have enough material to prevent failure.
Now, what about impact? When a load doesn't get applied gently but just hits suddenly. A shock load.
This is one of those great counterintuitive physics facts. A sudden load at the very instant it makes contact produces a unit stress and strain that is precisely twice what the same load would produce if you applied it gradually.
Double the stress for the same weight. No wonder shock loads are so destructive. Where does all that energy go?
It has to dissipate somewhere. The kinetic energy of that moving mass gets spread across four main areas: the deformation of the mass itself, the deformation of the structure it hits, conversion into heat, and absorption by the supports.
So designing for shock is really about designing for controlled, temporary deformation.
It has to be. If the structure were perfectly rigid, the stress would approach infinity.
Okay, we've covered how things break mechanically. Let's switch gears completely and look at the electrical world. From physical deformation to conductivity and thermal breakdown.
Agreed. And when we talk electrical materials, we have to start with copper. It's the benchmark. 100% IACS conductivity.
And the design consequence of that number is that it becomes the basis for basically all thermal management in power systems.
Any little deviation in the copper's purity or its temperature immediately throws off that fundamental calculation.
And when we size these conductors, we use a specific unit, the circular mil, the Shia mil.
Right, which is just the cross-sectional area. It's calculated as the square of the conductor's diameter in thousandths of an inch.
And for the really big cables.
We use mecmalium, where the m is just a multiplier for 1,000. So 1,000 mecmometer is simply 1 million circular mils. It's just engineering shorthand for when you're moving massive amounts of power.
Let's talk components, resistors. We usually just think about their wattage limit, how much heat they can get rid of, but there's another major failure mode.
The maximum continuous working voltage, V sub W.
And this is a really important distinction.
It's crucial. A resistor can fail from voltage breakdown, even if it's way within its wattage rating. The voltage itself, not the heat, destroys the insulating properties. You have to calculate V sub W.
Which is the square root of the power multiplied by the resistance.
That's the formula.
So let's do a quick example. A 100 ohm resistor rated for 200 watts. The absolute max voltage you can apply is 141.4 volts.
Right. And if your circuit runs at a higher voltage, you have to pick a physically larger resistor, even if it has the same wattage rating. It's about designing against two totally separate failure modes: dielectric breakdown versus thermal failure.
Speaking of dielectric issues, the other component famous for catastrophic failure is the electrolytic capacitor.
Oh yeah, they are notorious because they're polarized.
Hook one up backwards.
And you will very quickly release what we jokingly call the magic smoke. The electrolyte inside heats up, it boils, and the capacitor physically ruptures, sometimes pretty explosively.
Is there a good rule of thumb for sizing them in a power supply filter?
Yeah, a good starting point for a standard DC power supply filter is about 1,000 microfarads per ampere of output current to the load. That usually gives you a good balance between ripple suppression and, cost and size.
Okay, let's shift to AC, alternating current. Here we move beyond just simple resistance, R, and we have to introduce reactance.
Exactly. You have inductive reactance, X sub L, and capacitive reactance, X sub C. They define how a component resists a change in current flow. And together with resistance, they define the total circuit impedance, Z sub T.
And there's a critical frequency point where these two reactive forces meet.
The resonant frequency, F sub R, it's the point where X sub L is precisely equal to X sub C. They completely cancel each other out.
And at that point, a circuit can behave in really extreme ways, right? Huge amplifications in voltage or current.
Which has to be very carefully designed for. And finally, with AC, we have to evaluate the overall system efficiency using the power factor.
The PF. It's the true power you're actually using, measured in watts, compared to the apparent power, the voltamperes. In a perfect world, with a purely resistive circuit, PF is 1.
But in the real world, as soon as you add motors, transformers, any inductive loads, that number starts to drop.
So what's the engineering consequence of a low power factor?
It means the utility has to generate and deliver way more apparent power than you're actually using to do work. For a designer, that means you need thicker wires, bigger transformers, larger breakers, all to handle this reactive current that's just sort of sloshing back and forth doing nothing useful.
And the utility companies don't like that.
They hate it. Many industrial sites get penalized if their PF drops too low. They actually have to install huge banks of capacitors just to bring that number back up closer to 1.
Okay, now let's merge these two fields. Let's talk about devices that turn electrical energy into mechanical motion, starting with the workhorse, the solenoid.
Solenoids are fascinating because they have this dual current challenge. When the armature is far from the coil, that's its initial state, the device draws a massive inrush current.
Several times higher than what it needs later on.
Much higher. But once that armature pulls in and is fully seated, the coil's inductance changes, and you only need a much smaller holding current to keep it there if you let that big inrush current continue.
The coil is guaranteed to burn out. Thermal overload.
Absolutely. So how do DC solenoids prevent this?
With a really clever mechanical trick.
It's mechanical brilliance. They build in auxiliary contacts, sometimes called cutout contacts. They're wired in series with a large resistor, maybe two 100-ohm resistors.
And when the solenoid pulls that armature all the way in.
The armature itself physically opens those contacts, but that forces the current to go through the big series resistors, which immediately drops the current down to a safe holding level.
That is a self-regulating electrical protection system that's triggered by the very mechanical motion it creates. It's beautiful.
It is. But if that mechanism fails, you need a backup, a fuse.
And you can't use just any fuse.
No, you need a slow-blow fuse. A standard one would pop immediately from that required inrush current. The slow-blow type is designed to handle that initial surge, but is rated at, say, 1.5 times the specified hold-in current.
So it will blow only if the armature gets stuck open.
Yeah.
And that destructive inrush current just keeps flowing.
That's the safety net.
Switching these big inductive loads, solenoids, motors, it's absolutely deadly for relay contacts because of the inductive arc threat. What's happening there?
When you interrupt the current flowing through an inductor, its magnetic field collapses instantly. That induces a massive reverse voltage transient. It's a huge voltage spike.
And that high voltage creates a severe destructive arc across the contacts as they separate.
Especially with DC. There's no zero crossing to help extinguish it. That arc will literally weld the contacts together or just vaporize the metal over time.
So we need robust arc suppression. What are the main techniques?
Well, first, you can use a resistor-capacitor network, an RC snubber, across the contacts. The capacitor absorbs the transient energy, and the resistor limits the current flow.
Okay, what's another option?
You can use a varistor wired across the inductive load itself. It acts like a voltage clamp. It immediately shunts that transient voltage, limiting it to about twice the source voltage. Protects everything downstream.
And the third solution is wonderfully physical.
The magnetic blowout switch. You see these in heavy DC current applications. There are permanent magnets positioned right next to the contacts.
And when the arc forms.
The magnetic field puts a force on the ionized plasma of the arc itself. It physically stretches it and collapses it incredibly quickly. It literally blows the arc out, extends contact life dramatically.
Fantastic. Okay, finally, let's talk motors. The ultimate electromechanical machine. Engineers rely on standards here, like NEMA frames and insulation class.
Yeah, NEMA frames guarantee mechanical interchangeability. Standard mounting holes, shaft heights, that sort of thing. Insulation class, like say a class F, defines the thermal limit of the internal windings.
And for class F, that's 155 degrees Celsius.
It is. If you go over that, you rapidly degrade the insulation, which leads to short circuits and, well, failure.
How does a motor's theoretical maximum speed compare to its real-world performance?
We calculate the synchronous speed, the absolute theoretical maximum, by taking the frequency in hertz, multiplying by 120, and dividing by the number of magnetic poles.
But the actual full load speed of an induction motor is always going to be lower than that.
Always. That difference is called slip, and it's actually necessary to induce current in the rotor and create torque. No slip, no motor action.
For any large system, we also have to calculate the acceleration time. How long does it take the motor to get a heavy load up to speed?
This is critical for preventing thermal damage during startup. The calculation for the time, t, in seconds, depends on two big factors: the rotating inertia, which we call Wk squared, and the average torque available for acceleration, T sub a.
And there's a hard red line here that engineers have to watch out for.
Yes. If your calculated acceleration time is more than 20 seconds, you have to stop and reconsider the whole approach.
Why is that?
Running a standard motor at high current for that long during startup just generates too much heat. You'll trip thermal protection, or worse, you'll permanently damage the insulation, At that point, you need specialized motors or starters.
And even with all these precise calculations, engineers still sometimes go back to a very old-school method to verify performance.
The Prony brake, it's true. Despite all our complex computer modeling, the Prony brake is still a valid, hands-on way to use friction and levers to physically measure a motor's actual running torque and horsepower.
It's the ultimate reality check for the design specs.
It really is.
So we've covered a lot of ground. We've charted these essential data points for material performance, from standardizing failure with that 0.2% offset to understanding why a shock load doubles the unit stress, and right through to managing the integrity of complex systems like solenoids and motors.
Electromechanical engineering really is all about managing that energy conversion and the stresses it creates. Every single design choice is a trade-off. Mass versus inertia, conductivity versus thermal limits, durability against cyclic fatigue. A truly robust system is one where the electrical design fully respects the mechanical limits, and vice versa.
So, considering how critically all these material constants, like the modulus of elasticity and the geometric properties like moment of inertia factor into how long a design lasts, think about this. When you're calculating the power factor correction needed for a huge industrial plant, what's the real-world consequence if the ambient temperature correction factor you used for a component's max voltage rating was just slightly miscalculated? How reliant are our strongest, most efficient designs on the perfect constancy of environmental variables we can't fully control?